Welcome to my presentation. I'm Milad Zamani. I'm postdoc researcher at Aarhus University, and I would like to take this opportunity to talk about the idea on spiking neural network encoders. Here is my presentation on flexible energy efficient implementation of adaptive spiking encoder for neuromorphic processors. This work has been done at Aarhus University and was supported by the project named Hermes. So neural coding plays an essential role in enabling the brain-inspired SNNs to perform different tasks. However, the development of appropriate interfaces neural encoding is far behind the SNN progress itself. Here we propose a new encoder implementation that not only can be used the noise shaping technique, but also can accommodate different encoding algorithms such as slope-based encoding and step-forward encoding according to the how it is set. A further degree of flexibility is offered by an adjustable threshold. For each application, the algorithm can be selected and the threshold optimized in closed loop as the combination that maximizes the SNN performance in that specific task. This figure, the left one, shows block diagram of the spike encoder. The input of the proposed system consists of a sampling pass to the sampling capacitor and a history pass to the history capacitor. The system utilizes a four-input comparator that compares the input with the threshold voltage. A controller block generates different controlling signals based on a selected encoding algorithm. The proposed system provides both negative and positive spikes by utilizing a chopper at the input and the output of the comparator. The former chopper is responsible for generating spikes for both positive and negative threshold voltages, and the latter chopper assigns the polarity of each spike. Depending on when the history voltage is updated, many encoding patterns can be generated. The proposed system benefits from an energy-efficient dynamic comparator which only operates during the comparison phase. The same architecture can be used for higher-order noise shaping by using higher-order FIR filter as shown in the figure, the right side. The threshold can be adjusted based on the spike counting, averaging, or any method that does not make the encoder unstable. So here, the slope approach produces positive and negative spike encoding to the signal slope. The slope encoder compares the current sample input with the previous sample input each time. If the current sample is above or below a threshold, which is a minimal spiking slope, a positive or negative spike is emitted and the baseline is updated to the value of the current sample regardless of the firing of a spike. The step-forward encoder initializes a baseline for the first value of the signal. If the next sample will be at least as large as the threshold above or below the baseline, a positive or negative spike will be emitted and the baseline will be updated to the value of the current sample. The controller, the right figure, consists of a 45-degree phase delay, D-flip-flop ring oscillator, non-overlapping clock generators, and algorithm selection multiplexer. The non-overlapping clocks control the sampling switch, history pass switch, and the slope sign detection choppers. A multiplexer selects the encoding algorithm. So the proposed encoder is designed in a standard 180 nanometer TSMC process. The encoder covers an area of 50 micrometer by 65 micrometer. The left figure shows the simulation results of the proposed encoder in the step-forward encoding mode and the right one in the slope-based mode. The proposed encoder works at 1.5 voltage supply and it consumes 30 femtojoule per spike in a step-forward and a slope-based mode. The proposed encoder is very energy efficient since there is no static power consumption, and the dynamic comparator consumes power only using a spike, only during the spike generation. Thank you so much for watching my presentation.